The diagram you were shown in school is wrong, not simplified, not approximate, wrong, in a way that was chosen, not accidental, and the choice has shaped how every person alive thinks about where we live. There is a picture, you know it, 8 planets in a row, evenly spaced, all orbiting a sun that sits at the left edge. The planets are different sizes, color-coded, labeled. Neptune is maybe a thumb's width from Saturn. The whole thing fits on a page. That picture was never meant to show you the solar system. It was meant to show you the names. Those are different things. In 1966, a designer at the National Aeronautics and Space Administration named Laszlo Greenberg was part of a team preparing educational materials for the agency's outreach program. He sat at a drafting table with a set of measurements that had been known with precision for decades. He had the actual distances, he had the actual sizes, and he made a decision. If we draw this to scale, nothing fits on a page, not even close. The inner planets disappear, the outer planets become invisible. So he compressed. Every version of that diagram you have ever seen, in every textbook, every classroom poster, every museum placard, descends from that compression. The compression was practical. It was also a cognitive catastrophe, because a picture that cannot show what it claims to show should not be used to show it. Shrink the sun to the size of a grapefruit, roughly 14 centimeters across. At that scale, Mercury is about 6 meters away. Venus is 11 meters, Earth is 15 meters, Mars is 23 meters. So far, this sounds manageable. You could draw it on a long piece of paper. Then Jupiter enters. At grapefruit sun scale, Jupiter is 78 meters away. Saturn is 143 meters, Uranus is 288 meters, Neptune is 450 meters away. 450 meters, nearly half a kilometer, from a grapefruit. And at this scale, Earth is a grain of sand. Not the size of a grain of sand, an actual grain of sand, roughly 1.5 millimeters across. This is the picture that was too inconvenient to put in a textbook. The distances alone rewrite everything, but the distances are only the first layer of what the standard diagram erases. The second layer is motion. The textbook diagram shows planets in a line. Sometimes it shows them in a slight arc, as if they were arranged for a portrait. This is the deepest conceptual damage the diagram does. It implies that the solar system is a static arrangement, a fixed address where the planets can be found. In reality, the planets are never where the diagram shows them. They move. They move at different speeds, at different orbital periods, along ellipses that are not circles, around a center of mass that is not quite the center of the sun. Johannes Kepler worked this out in 1609. He was sitting in Graz with Tycho Brahe's observational data, decades of precise planetary positions recorded without a telescope, by a man who had rebuilt his nose from metal after losing it in a duel. Standing in the cold night after night with instruments he had built himself. Brahe's data was the most accurate record of planetary positions in human history. Kepler spent years trying to fit the data to circular orbits and failed repeatedly. The failure was not his, it was the assumption. When he finally allowed the orbit of Mars to be an ellipse, everything fit, not approximately, exactly. The diagram shows circles. The planets travel on ellipse. These are different shapes with different implications. On an ellipse, a planet moves faster when it is closer to the sun and slower when it is farther away. Earth in January, at its closest approach to the sun, is moving roughly 30 kilometers per second. Earth in July, at its farthest point, is moving roughly 29 kilometers per second. The difference is small. The principle it reveals is not. There is no constant speed, no fixed rhythm, no steady march around a circle. The solar system runs on variable geometry. There is something I find genuinely difficult to sit with here. Not the mathematics, which is elegant, but the scale of what the compression hides. I grew up with the standard diagram. I memorized the planet order. I took it as a map. And for years I thought I knew where I lived, that the solar system was a manageable neighborhood, that the planets were neighbors I could point to. It took until I first looked at a scale model, an actual physical one laid out across a field, to understand that what I had memorized was not a map at all. It was a legend, a key to a map that no one had ever drawn. The loss is not trivial. A map that cannot be drawn to scale is a map that cannot be used for navigation. And everything we feel about our place in the solar system, the intuitions about distance, duration, reach, isolation, comes from the picture we were given. The outer solar system does not end at Neptune. The textbook shows Neptune as the final planet, which is technically accurate. Neptune is the final planet. But the edge of Neptune's orbit is nowhere near the edge of the solar system. Beyond Neptune lies the Kuiper Belt, a broad ring of icy bodies extending from roughly 30 astronomical units from the Sun to about 50 astronomical units. An astronomical unit is the average distance from Earth to the Sun, roughly 150 million kilometers. The Kuiper Belt alone extends to 7.5 billion kilometers from the Sun. Pluto lives in the Kuiper Belt. When Clyde Tombaugh discovered Pluto in 1930 at the Lowell Observatory in Flagstaff, Arizona, scanning photographic plates in a blink comparator, looking for a point of light that moved against the fixed stars, he was not finding the edge of the solar system. He was finding the beginning of a second solar system that no one had suspected was there. The Kuiper Belt contains hundreds of thousands of bodies. Some are as large as small planets. Eris, discovered in 2005 by Mike Brown and his team at the Palomar Observatory, is actually slightly more massive than Pluto. Brown spent months running orbital calculations before he was certain of what he had found. His team's discovery is what triggered the reclassification of Pluto, not politics, not sentiment, but the mathematics of a population. You cannot call one object a planet and refuse the same designation to 50 others with identical characteristics. Beyond the Kuiper Belt lies the scattered disk, a sparse population of bodies with highly elliptical orbits, some reaching hundreds of astronomical units from the Sun before swinging back. Sedna, a body discovered in 2003, has an orbit so elongated that at its farthest point, it is roughly 1,000 astronomical units from the Sun. Its orbital period, the time it takes to complete one circuit, is approximately 11,000 years. Sedna was last at this point in its orbit when humans were first beginning to develop agriculture. Chad Trujillo and Scott Shepard discovered Sedna using data from the Samuel Oschin telescope at the Palomar Observatory. When they ran the orbital mechanics and got that number, 11,000 years, Shepard reportedly sat back and stared at the screen for a moment. There was no immediately obvious explanation for an orbit that extreme. There still isn't. One hypothesis is that a passing star disrupted the outer solar system billions of years ago. Another is that there is a large undiscovered planet in the far outer system, what astronomers currently refer to as Planet 9, whose gravity sculpts the orbits of objects like Sedna. As of today, that planet has not been found. And beyond the scattered disk, if current models are correct, lies the Oort cloud. The Oort cloud is not a disk. It is a sphere, a roughly spherical shell of icy bodies surrounding the entire solar system at distances between 2,000 and 100,000 astronomical units. At its outer edge, the Oort cloud is roughly 1/4 of the way to the nearest star. Jan Oort proposed it in 1950. He was at the Leiden Observatory in the Netherlands, working through the orbital data of long-period comets, comets with orbital periods of hundreds or thousands of years, arriving from all directions in the sky. If they were arriving from all directions, their source had to be a roughly spherical reservoir. He calculated where that reservoir had to be, how large it had to be, how many bodies it had to contain. The numbers were enormous, and the structure was entirely unobservable from Earth. The Oort cloud has never been directly observed. We know it exists because the comets that pass through the inner solar system have orbital histories that require it. They carry the signature of a distant origin. But the cloud itself is invisible. Every map we have of it is inferred, not drawn. At the scale of our grapefruit sun model, with Neptune at 450 meters, the inner edge of the Oort cloud would begin roughly 600 kilometers away. Its outer edge would extend to 30,000 kilometers. The solar system at human scale is not a neighborhood, it is a continent. The diagram shows a page. The difference between the textbook picture and the actual structure is not a matter of precision. It is a matter of kind. The textbook picture implies a closed system, 8 planets, fixed arrangement, visible boundary. The actual solar system is an open, dynamic, partially unmapped structure extending to distances we have never traveled, containing populations of objects we are still in the process of discovering, with a boundary that keeps moving outward every time we look harder. In 2015, when the New Horizons spacecraft flew past Pluto after a 9-year transit, a spacecraft the size of a grand piano, crossing a void so empty that during the entire transit, it passed no object larger than a dust particle. The team at the Johns Hopkins Applied Physics Laboratory watched the first close-up images of Pluto come through and found mountains. Mountains of water ice 3,000 meters high, a heart-shaped nitrogen glacier the size of Texas, a surface geologically active on timescales that required an internal heat source no one had predicted. Alan Stern, the mission's principal investigator, had spent 26 years pushing for that flyby against institutional resistance, budget cuts, and 2 cancellations. He was in the mission control room when the images arrived. He did not say anything for a moment. He had spent more than 2 decades knowing, intellectually, that Pluto would be complex. The image still surprised him. That is the thing about scale. You can know the numbers. The numbers do not protect you from the surprise of the actual. There is a direct line between the diagram and the surprise. If you grow up with a picture that places the planets in a row that compresses 4 billion kilometers into 6 inches, that shows Neptune as a small blue circle a thumb's width from Saturn, you carry a feeling about the solar system that no amount of reading corrects. The feeling says, this is small enough to picture. This is a neighborhood I could mentally walk. The planets are close enough to be neighbors. The feeling is wrong. Not approximately wrong. Wrong at the level of order of magnitude. The New Horizons mission launched in January 2006. It traveled for 9 years at a speed of roughly 58,000 kilometers per hour. At that speed, you would cross the continental United States in about 4 minutes. 9 years of travel at 4 minutes per continent, and the spacecraft reached the first object in the Kuiper Belt. The inner solar system, the part with all the planets, the part the diagram shows, represents roughly the first 1% of the solar system's actual radial extent, if you define that extent as the outer edge of the Oort cloud. Everything the diagram shows is the first percent. We build spacecraft to explore our solar system. We plan missions with decades-long timelines, billion-dollar budgets, international partnerships, and those achievements are real. The spacecraft Voyager 1, launched in 1977, still transmitting from beyond 23 billion kilometers away, is the farthest human-made object in history. But Voyager 1, at its current distance, is still within the inner Oort cloud's theoretical reach. It has not left the solar system in any meaningful sense. It has crossed the heliopause, the boundary where the sun's particle wind gives way to interstellar medium. But the gravitational influence of the sun extends far beyond that. The spacecraft will not escape the sun's gravitational reach for another 30,000 years. 30,000 years. The diagram made us feel like we were near the edge. We are not near the edge. We have barely moved. The edge of the solar system is not a line. It's a question we keep redrawing, and every time we move it further out, we find that the system we thought we knew was only the part we could see from here.